Okay, well, as the title says, it is much less sophisticated than what you have just been hearing from Dr. Maffei. It is of the level of sophistication of the hula hoop, but then the hula hoop had some success. We can't deny that. And also the funding scales also like the hula hoop as compared to the funding that Dr. Maffei had. So the basic idea is indeed very simple. You have a circularly polarized source that you send through a portion of high birefringent, which is actually a polarization preserving fiber. And at the end, you send the polarizer, you send the light to a detector through a polarizer. The result actually is that you can measure temperature changes less than 20 millikelvin or millidegrees centigrade, depending on the range depending on the angle of that polarizer that you put. Here is the normalized transmission versus temperature, and you can see that here between these 2 points there are 20 Kelvin or 20 millidegrees centigrade. You can also use that to measure, to our surprise in fact, the power of the laser beam sent through the fiber. Here is changes of power in the milliwatt range, and you can see that the polarization characterized by a polarization ellipse, the angle of the ellipse changes and the ellipticity changes. And from that, you can infer the power. In fact, that power change is due to a slight change in temperature of the fiber core, and this is calibrated here, the power change versus the temperature that it produces. So the background is simply that polarization preserving fiber, if you send in that fiber any light that is not polarized linearly along the axis, its polarization is going to change periodically over a very short beat length, as it is called, while the fiber length can be hundreds or thousands of beat lengths. So if there is any thing that produces a minuscule change in beat length, that change in beat length get decoupled in a macroscopic length of fiber. So the basic measurement is sending light from a diode laser through a quarter wave plate that makes it circularly polarized, sent through that is a sensor, this PM fiber, a couple of centimeters, a rotating mount to analyze a polarization, and a detector. And the result of the measurements are, as this polarizer rotates, some pretty 8 pattern from which we can determine all the characteristics of the polarization. Here is a temperature measurement that shows a transmission versus fiber core temperature taken for a particular angle of the analyzing polarizer. These are actually the raw data that shows these polarization ellipse changing. And this picture here is in the temperature is in false color. Really false because the red is the hot part and the blue is the cool part. That should be the other way around, sorry. But you can see that for a particular angle of the polarizer, we have a nearly linear change in transmission at different angles, at different slopes. Application, well, the advantage, it has very low power consumption, sensitivity to temperature change in millikelvin, which I think we can improve. this can access most remote location. There are no metallic components, so there is no sensitivity to electric field or to magnetic field, to high voltage, etc. And surprisingly, for a thermal device, it has a response time in the microsecond range, under 25 we measure, and that can also be improved. And another advantage, more sophisticated here, is this is the only way to access directly the core of the fiber, which has minuscule dimension in the micron. So that may have a specific need for fiber-based radiation balanced laser, which is an area of research of Dr. Murphy. And so in that case, for the high power laser, there are methods to be developed to increase the cooling of the core through radiation transfer. But for that, you need to have a means to measure the temperature core, and that is what this is about. So the temperature measurements, some requires fast response, and so we measure that response time by sending a stepped a pulsed laser, square wave pulses, and seeing at the transmission that shows a jump in temperature and then a cooling, the time constant of these two time constants. And in fact, the slowest response time that we measure is indeed under 25 microseconds. So to be compared to what exists, there are Bragg grating temperature sensors, which are also in fiber. They have a response time in the minutes rather than in the microseconds. Other application is the stabilization of some fiber lengths in interferometer, in laser, in frequency comp, in time standard. And just to illustrate how that works, there is here an example of a Michelson interferometer, which has an arm where you want to do measurements and a reference arm. Then you use another laser beam that is this green line that you send through that same polarization maintaining fiber, a detector that measures a polarizer, and a detector that monitors the temperature. How do you stabilize? But, well, the power of this laser is a control device to get the temperature. So the output of the detector can be sent through a feedback loop onto that laser to stabilize the length of this arm. So, well, market is a big question mark. This is a simple fiber length stabilization for frequency comp, interferometer, and laser. It is a simple fiber power monitor. It's a temperature sensor or monitor for objects in a high field environment. It can also be used as a surgical absorber with ultra low power level saturation. In fact, company Torr Labs is interested in that aspect. It can be used for monitoring the fiber core temperature for high power laser research. And it can be for temperature sensing where fast response is required. Well, that temperature sensitivity in the millikelvin range, there are means to improve that by increasing the length of the fiber. One would like to increase the dynamic range because we are looking at temperature change in a small range. It has an optical power sensitivity in the milliwatt range. Can it be extended to microwatt? That is a question to be answered. It's probably possible by doping the fiber. Response time in the 125 microseconds. Tapering the fiber should lead to faster response time. And it's a surgical absorber at the milliwatt level. faster response and lower saturation would be desired for application, but it's quite possible. And yes, we don't have direct funding at this point, except the pending Small Business Innovation Grant from NASA.